Okay, so hello everyone. So we are very happy to have Professor Seok from Seoul National University as our colloquium speaker. So let me briefly introduce him. So Professor Kim got his PhD from Seoul National University in 2004. And after that, so he spent some time as a research fellow at KIAS and research associate at Imperial College London. Then he joined Seoul National University as a faculty in 2009. And Professor Kim has published many influential papers on non-perturbative aspects of quantum field theory and string theory. So he received Nishina Asia Award in 2016 so due to his outstanding works on supersymmetric gate theories in various dimensions. So in his recent research, so he has explored emergent gravitational phenomena of QFT and microscopic descriptions of quantum gravity. So today, so he will tell us about his recent works on black holes and quantum gravity. So please start.
Okay, thank you, Tatsuma, for the kind introduction, and also thank you for the invitation to this colloquium. I'll be talking about some thoughts that I've had on black holes and its relation to various key aspects of quantum gravitational theory. Most of the talk actually will not be based on what I have actually worked on, except a little bit of stuff at the end. Yeah, so I'll try to explain how certain aspects of black holes, the quantum and thermal aspects of black holes, have direct connection to the key properties of quantum gravity itself. So black holes are obviously one of the most mysterious predictions of general relativity, but by now we are confident that these objects are ubiquitous in the sky, and especially in the modern days. It's really a high time for the observational black hole physics at various sizes and scales. But today what I'd like to talk about is about conceptual aspects of the black holes and rather mysterious aspects of black holes that has been puzzling people for more than a century, from early 20th century when the black holes solutions are discovered. And I'd like to discuss how these mysterious aspects of black holes provide an interesting window to better and solidly understand the foundational aspects of gravitational theory, especially the quantum gravity. So black holes are strange conceptually for many reasons. One thing that has been puzzling people from early days is that the fact that it has singularities in the structure of our space-time at the center of the black holes. Another aspect, which is more circular, is that it has what's called the event horizons, okay, beyond which an outside observer cannot see. And the focus of my today's talk will be the consequence of the black holes having event horizon. And I have basically nothing to say about the singularities of black holes. So the event horizon arises because if there is a very massive matter condensed in a specific region to form black holes, the gravitational effect is so strong, so they bend particles and light in such a strong way that there is a region near black holes in which any events, particles or lights inside it cannot escape out of this region to the outside, to be visible by outside observers. So we call this region in which the particles and lights cannot escape, we call the boundary surface of this region the event horizon. The reason for the name being that if you see the black holes from outside, and if any events like particles or lights enter into this inside region, the outside observer can no longer see such an object. So it's really like horizon, the sea or the land. The obvious consequence of having event horizon is that an outside observer loses information about what's going on inside let's say, about the matters inside this black hole. So the information behind the event horizon is not visible by the outside of observers. So due to the fact that certain observers are not given accessibility about the matters inside the event horizon, the observer is only given a very limited number of information about the matters forming black holes, like the masses, charges, and the spins, angular momentum. And at this moment, if you think about the basic disciplines of physics at the undergraduate level, there's one discipline, subdiscipline of physics, which deals crucially with the inaccessible information in physics, and that's called the statistical physics. And as I'll try to introduce to you, I mean, most of you will know, but just to remind, the inaccessible information caused by the presence of the event horizon has very close connection to do with the statistical physics, which also deals with the lack of information of an observer about the system. So the statistical physics stems from the practical attitude that if you deal with a very macroscopic system, it's very impractical to seek for all the atomic information about this system. So unlike seeking for all the microscopic information, people focus on specific information like energy, temperature, pressure, volumes, and try to describe the systems with this limited data given, which leads to thermodynamics, whose theoretical foundation is called statistical physics. And in this kind of discipline, the underlying master quantity of describing thermodynamics may be understood to be the entropy, which measures the ignorance about the system by the observer. So at fixed values of certain limited information given, one counts the number of possible states at these fixed extensive quantities, and we call the log of this number of accessible states, which is generally not unique, as the entropy. So once you know this master function, you can manipulate this function with respect to these variables to investigate other interesting physical quantities. And in the presence of black holes, you're forced to have some information lacking, and quite surprisingly, but also a bit naturally, the fact that you have certain information missing due to the presence of event horizons of the black holes induces a thermal behaviors in the gravity in the physics of black holes. So that has been established from quite long ago, from late 60s or early 70s, by the pioneers' work like Bekenstein, Hawking, and people, that the black holes are respecting certain laws similar to the basic laws of thermodynamics. For instance, if you perturb the black holes slowly by, let's say, throwing in some matters carrying charges, and if you observe the change of the mass of these black holes, which has observed these extra matters and so on, this change of mass can be regarded as change of energy due to the equivalence principle, and it obeys a behavior very similar to the first law. So certain changes of masses can be accounted for as walks. If you throw in certain charges or something, it has certain walks, okay? But there are some part of the energy which you cannot explain obviously as a walk function, and that formally takes a form similar to the so-called heat in quasi-static processes. So kappa is the surface gravity of the black hole at the event horizon, and A is the area of this event horizon, which is often given by a two-dimensional sphere. And it's similar to the heat if you view this surface gravity as analogous to temperature, and this area of event horizon as being analogous to the entropy. It also obeys the second law. If you try to survey the consequence of the evolution of black holes with event horizons, under general, very mild assumptions, it obeys the conditions that the area of the event horizon never decreases, something like the second law of thermodynamics. And Hawking's discovery of Hawking radiation really implies that this should be seriously regarded as real thermodynamics rather than just analog concepts. Because Hawking has established that if you consider the effect of quantum physics near the black holes normally is expected to radiate out a tiny little bit of thermal radiations, with its temperature actually proportional to the surface gravity. And he has fixed the proportionality constant of Hawking temperature, and thus the relation between the entropy and area has been fixed at this way. So we are seriously suggested to consider this kind of thermodynamics as being real thermodynamic behavior of black holes. Okay. So I'm going to try to explain to you what are the simple consequences of these thermodynamic interpretations of these black holes would be on the underlying quantum gravity itself. Really seriously trying to interpret this area entropy as reflecting the number of microscopic degrees of freedom of the matter lurking inside this event horizon of the black holes. So if you try to look at the detailed behavior of this what's called the Beck-Einstein-Hawking entropy for the black holes, it behaves very exotically. It behaves exotically in the following sense. I'm going to explain in this slide. And you can get a better feeling just by having a look at the simplest black holes, the Schwarzschild. Anybody has questions?
Yes, actually, I have a small question about the previous slide.
Yes, please. Yeah.
Yeah, this one. So you seem to be taking the perspective that we're thinking of thermodynamics as being sort of obtained from statistical physics, but there's also this viewpoint of just thermodynamics as a theory of its own. I think it was developed by like Lieb and I can't pronounce the other name, I'm sorry. And in that sense, does this actually fit within those axioms of like that perspective on thermodynamics, where because you say here it should be real thermodynamics, and I'm assuming you're saying real in the sense that we should be able to understand the microscopic degrees of freedom that let us use statistical mechanics to show that it's a part of thermodynamics. But if I just view it as thermodynamics on its own,
you mean not worrying about statistical origin at all?
Yeah, if it rigorously conforms to a theory of thermodynamics, for instance, as set up by that theory.
Well, maybe possible, but well, I'm not really saying that we are forced to accept this direction, but compared to the 19th century thermodynamics, in which we didn't know statistical mechanics about macroscopic systems, everybody got happier. So since it really behaves like a thermodynamics, maybe the phrasing was not really nice. Since it really exhibits a dramatic phenomena of thermodynamic behavior, like black body radiations and so on, I meant to say that it's more natural to seek for the statistical origin of this phenomena. And yeah, that was what I really wanted to say. And if you accept this kind of direction, it will really say something more very microscopic about the underlying quantum gravity, its number of states at large charges or so on. So yeah, maybe my phrasing here was a little bit misleading.
No. I think we're on the same page. I just wanted to clarify. Thank you.
Yeah. I just wish to say that it behaves in all ways similar to the thermodynamical system that we know well around us. So along the same line, we want to seek for statistical origin and really seriously regard it as a statistical physics system. Is that better?
Yes, thank you.
Okay, thank you for the clarification. And I'd like to explain to you, if you really view this as a statistical entropy, counting number of certain states at certain energy, it behaves very exotically. It starts to behave unlike the thermodynamic systems around us. It's odd in the sense that it has a negative specific heat if you view mass as the energy carried by the black holes. It's very easy to see that for Schwarzschild black holes, let's say in 3+1 space-time dimensions, the Hawking temperature is computed to be inversely proportional to the mass. So if you increase the energy, temperature decreases and vice versa. So it's saying that it has negative specific heat. It's quite a general property of the black holes in all general dimensions, let's say in 4 or higher dimensions, where gravity is typically dynamical in full-fledged form. So if you just try to understand the relation between the entropy and mass, the entropy is scaling as an area, so r to d minus 2, where d is the space-time dimension. But the mass is scaling in 1 less power, coming from the form of the Newton potential scaling in the given dimension. So from this negative specific heat stems from the very simple fact that entropy is a concavely increasing function of mass. So let me say that this is a very fast growth of mass. So entropy is a growing function of energy. It's an increasing function, but it's not just an increasing function. It's a very fast increasing function if you go to high energy regime. So it's a convexly increasing function. That's what gives the negative specific heat, because the inverse temperature is the first derivative. So the positivity of the first derivative means that temperature is positive. The positivity of the second derivative means that inverse temperature is an increasing function of energy, meaning that the temperature is a decreasing function of energy. So the negative specific heat stems from the fact that entropy as a function of energy of the black hole is a very fast increasing function of energy. Okay. We do occasionally encounter such systems around us, not often, but occasionally, like the physics of collapsing stars. The star radiates energy and shrinks, but its temperature grows. So we occasionally encounter that. But in any case, if you really want to interpret this entropy of black holes as representing fundamental degrees of freedom of the full quantum gravitational systems, of the matters behind the horizon, it raises rather puzzling implications. Fundamental degrees of freedom carried by some matter systems at this energy. Well, most technically, the system with negative specific heat is known to be unstable in canonical ensemble at fixed temperature. Well, it's not really clear what it means by trying to, well, canonical ensemble is a system obtained by coupling a given system with a very large heat bath so that the temperature is fixed. Well, fundamentally, I don't know what it really means to couple the whole universe to a very big heat bath. But anyway, it's always what one can conceptually think about. And if the system has negative specific heat, you're not allowed to do that. It's unstable by small fluctuations. Of entropy as a function of energy demands an unusual structure of the Hilbert space of quantum gravity itself, in that it demands a very fast growing entropy in the high energy regime set by the Planck scale. So I'm going to study some consequences of this demand, closely related to how quantum gravitational physicists have accounted for this black hole entropy microscopically in a consistent model of quantum gravity like string theory. So let us think a little bit more about this exotic entropy, of very fast growing entropy, a concavely growing one. You can easily convince yourself that such a fast growing entropy at high energy is very unfamiliar in standard particle physics. For instance, if you consider the relativistic particles in these spatial dimensions at high energy, you can basically regard it as massless particles. Okay. For instance, if we consider free massless particle, well, you can just directly compute the entropy. More generally, on dimensional grounds in natural units, you can decide the behavior of the entropy and energy scaling in the temperature just on dimensional grounds, because entropy is dimensionless and scales with volume. This temperature dependence should be this way. Energy should also be this way. So if you compute the entropy from the scalings, it's an increasing function of energy, but always a convexly increasing one. You know, the exponent is smaller than 1, so it's a convex increasing function. So it grows in energy, but not too fast, meaning that the specific heat is positive. So it's quite hard to imagine what kind of system will have fastly growing entropy. It's basically made possible if you have infinite species of particles. Okay, so the entropy grows faster than this given number of particle system. This kind of fast growth, I mean, much faster than convex growth, is somewhat familiar in quantum theory of gravity. For instance, string theory has been long sought after as a consistent description of quantum gravity. And string theory has many more high energy degrees of freedom than particle physics. So long ago, it really stems from the works by Hajidon in 1960s, which was actually the work on strong interactions and mesons, but it has been reinterpreted in early 80s in the framework of string theory. If you consider the excitations, high energy excitations of elementary strings, its entropy, or more precisely the density of states, scales linearly in energy. Okay? So it's linear is borderline of being convex and concave. So anyway, it's much faster growth than the convex growth of the particles entropy like this. So if you consider string theory, suddenly it shows a much faster growth of the high energy entropy. And it's really due to the infinite tower of string oscillation modes. So strings are roughly identical to an infinite tower of particles with ever increasing masses. And we call this kind of linear growth as a Hajidon growth. It's not yet concave, but it's really at the borderline of entering this region. And this kind of concept was originally discovered in the context of hadron physics. You have infinite towers of mesons. And if you regard all these mesons as following Regge trajectory as fundamental particles, you get this kind of growth. It's a much faster growth than particle physics. Still, it's the entropy carried by the fundamental or the perturbative strings, but it's still not fast enough in that the linear growth is much slower than the concave growth that we expect for black holes. So it gives a strong signal that to find a microscopical account of the black hole entropy, which is a convex growth, concave growth, if you want to seek for such an explanation in string theory, presumably you need to include non-perturbative degrees of freedom beyond the elementary strings. Okay, so that kind of huge number of extra degrees of freedom can be provided, let's say, by string theory, because string theory has lots of non-perturbative objects. And for instance, the object that has been playing important roles in the history of counting black holes is called D-branes. They're like solitonic objects in string theory. So once you introduce these solitonic objects, you can form bound states among themselves. You can form extra bound states with the elementary strings. And the number of degeneracy of these bound states grows much faster than those of elementary strings. And it suddenly turns out to be concave. So these brane objects have been introduced by Polchinski in mid-90s. And right after that, people have studied the elementary quantum mechanics of these bound states of these non-perturbative objects in quantum gravity. And they have found concave behavior of entropy, which in fact agrees perfectly well at the macroscopic level with the Beck-Einstein-Hawking entropy of black holes. So for technical reason, people have sought after the statistical picture of this area law of black holes in a technically calculable examples of what's called extremal black holes, and more precisely BPS black holes, which preserve certain supersymmetries of the superstring theory. Anyway, in this kind of extremal black holes, is a special kind of black hole which carries not just energy, but also electric charges. And it carries a very special property that the mass of this extremal black hole is given by the charge that it carries with a specific coefficient. So in this kind of black hole, charge is playing the role of mass. So many aspects of these extremal black holes are different from Schwarzschild black holes, in that it doesn't Hawking radiate or so on. But entropically, if you want to study the high energy degrees of freedom, remembering the fact that charge is playing a role very similar to the mass, the concave growth is very similar to that of the Schwarzschild black holes, or semi-quantitatively similar. So this kind of microscopic account of the entropy of such black holes has been done in various dimensions, where entropies in terms of charge or mass is given in this concave form. And if you look at this power of Q in various dimensions, it's precisely the same as the mass dependence of the Schwarzschild black holes in the same dimension. If you plug in 5, you get the same power here. If you plug in 4, you get the same power here. So it not only explains the statistical origin of the black hole entropy in quantum gravity, it reassures to us that indeed in these quantum theories of gravity, the high energy entropy exhibits a very fast growth due to the non-perturbative bound states like d-branes and so on. It's a concave growth. And similar to the fact that the black hole, if you view it as a thermal system, can be studied only in microcanonical ensemble, these systems can also only be studied in microcanonical ensemble as well. For instance, if you study them in grand canonical ensemble, due to the convex nature, concave nature, the susceptibility is negative and the system is unstable. So it reassures to us that in the high energy region or high charge region, the number of states or the density of states should be huge, very fast growing.
Sorry, can I ask one question?
Please. Yeah.
So this instability is in the grand canonical. So
Yeah.
let's see, for example, in what kind of the perturbation makes the system unstable in more concretely?
You know, if you couple it to not just a heat bath, but to a bath in which you can exchange the particle numbers and charges.
Okay, then it's
the thermal fluctuation instability makes this system unstable if you couple it to the bath.
So that changes the number of the charge of the black hole. Is that right? Essentially.
The changes the charge of the black hole, but if you perturb it a little bit, it may want to come back to its original configuration, or it may be destabilized.
Right.
If the susceptibility is negative, if the system is destabilized by small exchange.
I see. I see. Yeah. So it ends up with a black hole with a different charge. Is that right? Is that what they said? I mean, number is not conserved system, then it's become unstable. Is that right?
I think what is the endpoint of this instability could be. I think it just forces you not to consider it in grand canonical ensemble if you want to do a thermodynamics with this. I mean, I think it just means that it makes sense to do thermodynamics only in the micro canonical ensemble with fixed charges.
But what's wrong with if you consider the system where you can exchange a number with a particle?
If you couple it to a very large heat bath, it's not a stable system.
Right.
It's not a stable system.
Right.
So.
Okay. Thank you.
Yeah. So, any other question?
Can I ask one related question?
Please.
So in your previous example, so you consider BPS black hole,
yes.
so which is supposed to be stable in the sense that it is lowest energy state. And so I wonder, so how this instability is related to?
Probably means dynamical stability.
Dynamical. Oh, I see. So you mean
dynamical stability, but this stability is a little bit different notion. You couple it to an artificial, a very large heat bath, and allow some exchange due to some thermal fluctuation, and it's an instability in this sense. So thermodynamical instability very often appears in BPS black holes as well. Yeah, although it's not related to dynamical instability. Yeah. Well, it simply forbids you to consider it in the particular thermodynamic setting of this black hole.
Yeah. Okay, thank you very much.
Yeah. So this fast growth of black hole entropy, I'd like to emphasize, is that intimately related to the fundamental structure of the Hilbert space of quantum gravity. Well, at least in string theory models that we have considered. That's interesting because historically, we have been considering string theory as a model of quantum gravity because string theory cures the technical inconsistencies of Einstein's general relativity as a quantum theory, coming from the UV divergences and all the technical things. And the way string theory cures the general relativity's quantum UV divergence is by introducing an infinite number of extra degrees of freedom. So instead of just exchanging gravitons, there are some channels exchanging all the excited particle modes of strings, and that cures the infinite ultraviolet divergences of quantum gravity. So historically, the way of motivating strings with infinitely many extra degrees of freedom, which is one reason which makes string theory exotic, was very technical one. Now we may also understand that this is a constraint required by the quantum black hole thermodynamics, if you try to interpret this seriously. It demands that the entropy is really fast growing. So to account for that microscopically, quantum theory of gravity had better have huge number of extra degrees of freedom than those visible in Einstein's relativity. Okay. And with this viewpoint, I think it would be interesting to review how other models suggested for quantum gravity view the black hole thermodynamics, especially focusing on the number of fundamental degrees of freedom they have beyond general relativity. I have no concrete things to say about this because I am largely ignorant about many other proposed suggestions about quantum gravity apart from string theory. I have little thoughts about higher spin gravities, but largely it's a kind of question I'd like to consider in the near future, having this particular viewpoint in mind of black holes. For instance, there are many alternative ways of generalizing general relativity. Let's say there are certain higher spin gravitational theories, which also have infinitely many fields, but in a rather different nature from the extra degrees of freedom of string theory. There are some loop quantum gravity, or there's some suggestion about the asymptotically free quantum gravity based on the idea of UV fixed point. I think it would be interesting to understand how these models, if any, try to understand the physics of black hole thermodynamics, having the story I presented to you so far in mind. So I think that would be a very interesting thing. But yeah, that was just a small comment. So I tried to establish to you that the fast-growing entropy of black holes is related to the structure of the Hilbert space of quantum gravity.
Can I ask you a question?
Please, yes.
In the previous slide, can you comment on a bit more about what do you mean by a bit different natures from strings for higher spin gravity?
Oh, it has infinitely many fields other than the metric, I think, but they are massless fields, right? In ATS, strings come in a massive tower. I mean, whose masses are following certain reguli trajectories or so on. But for higher spin gravities, it's slightly no, it's not registered. You know, in the sense that the infinitely many fields or particles in string theory come in a tower that they are given increasing masses if you go to higher species of the tower. But higher spin fields in gravity are not of that sort. I mean, I think they are massless, enjoying certain higher spin gauge theory. So they have rather different natures than strings. And it has enlarged
those kind of different natures.
Those kind of different natures
reflected what kind of properties of black holes?
The thing is that if you study the higher spin gravities, first of all, I don't think it's very well formulated at I mean, some equation of motions are given in very complicated form, but I think concrete studies of black holes in higher spin gravity is very limited. The only thing I know very well is the lower dimensional gravity, let's say in ATS3 or something, in which you can make very rigorous studies of higher spin gravities. And there, due to the presence of higher spin gauge symmetries and so on, it's very hard to establish what the black hole entropy itself is. From, you know, you cannot really say it's following area law, because I think the notion of event horizon itself is gauge dependent in higher spin gravity. So giving a precise sense of black hole thermodynamics just from geometry becomes more circular in higher spin gravity, if I understand correctly.
I see. Thank you.
Yeah. So, well, yeah. So anyway, I try to establish these facts, but now I'm going to consider the conceptual shortcomings of these black hole as a thermal systems. So I try to emphasize to you that the black holes with fast-growing entropy makes no sense if we consider them coupled to a large heat bath in canonical or grand canonical ensemble. And this makes some of the very interesting thermodynamic questions irrelevant or just ill-defined. And I want to improve the situation in which this kind of canonical or grand canonical problems could be well defined in quantum theory of gravity, because they are related to some other fundamental questions of quantum gravity that I'd like to explain to you from now. And the fact that these thermal systems are exotic, not making sense in these ensembles, turns out to be very closely related to the certainties of string theory and quantum gravity at high energies. It often is related to the fact that if we increase the temperature, the system may want to be in a new phase after undergoing a phase transition. A similar thing happens in QCD, where I explained to you the Hadron growth in a few pages before. So this Hadron growth of mesons or hadrons is not concave, sorry, where's that? It's just linear growth. But since it's much faster than ordinary particles growth of entropy, if you increase the temperature beyond the critical temperature, it becomes subtle or doesn't make sense to couple this system to a large heat bath and consider that this system is in a fixed temperature. So this kind of question arises if you try to regard the hadrons in QCD as fundamental degrees of freedom, rather than a composite object made of quarks and gluons. So what happens in QCD is that beyond certain temperature, a phase transition happens, after which the quark and gluon degrees of freedoms becomes the right variable rather than the hadrons. The number of degrees of freedom decreases a lot beyond this high temperature phase transition. And at high temperature, the system is described by a plasma of quarks and gluons rather than this tower of hadrons. So a similar problem of having certainties in defining this canonical ensemble is related to the fact that the system is undergoing a phase transition at high temperature. So a similar thing will be happening in gravity, suitably defined. A more general certainty about considering the gravity at fixed temperature is that when the temperature is fixed, the extensive quantities are supposed to be growing like the size of the system, like the volume. So you need to set up the finite volume version of the quantum gravitational problem. Or in other words, you need to introduce certain infrared regulators. Okay? If you consider some ideal gases at fixed temperature, you always introduce a box which serves as a finite size. Okay? If you fix the value of the extensive quantities, as in microcanonical ensemble, that's it. But if you fix temperature, which is an intensive quantity, all the behaviors of extensive quantity, not fixed, should behave as the size of this infrared regulator. But for gravity, you cannot artificially put this system in a box as you wish, because everything, including the box, is subject to equivalence principle. So you have to, if you want to introduce this infrared regulator of a finite size box, you have to do it very judiciously, respecting the general principle of equivalence principle of general relativity, including this box of systems. So now I try to present a simple model which sort of introduces a gravitational box or trap for the general relativity in a consistent manner. I mean, consistent with the equivalence principle and so on. And that one way of doing that is to consider the quantum gravitational system in a curved background called anti-de Sitter spacetime. So it provides a theoretically consistent setup for putting the system in a finite box, more precisely a confining gravitational trap. Okay? You won't have an explicit volume form, but the system is confined in a finite region. So many subtle thermodynamic concepts will certainly make sense if you consider the system in antidistance space-time. So it's represented by a particular form of the metric with the time and the radial direction and the transverse sphere direction, if you consider d plus one dimensional antidistant spacetime. Well, technically it's what's called a global ADS, but it won't matter too much here. The property of this spacetime is that it confines all the massive objects, including black holes, to the central region, and it prevents all these massive objects from escaping to infinity because of this gravitational attraction factor. Very roughly speaking, it's an abuse of Newtonian gravity, but very roughly speaking, if you consider the TT component of the metric, it's roughly like the gravitational Newton potential, and it really wants to hold the massive particles near the central region rather than going to infinity. And it renders many thermal questions of quantum gravity well defined. So that's the setting in which I'm going to explain certain interesting variations of the black hole thermodynamics problem, which will also shed interesting light on the microscopic nature of quantum gravity, especially at high temperature. Incidentally, I introduced, well, antidistant space-time as a providing a finite box or infrared regulator of doing thermodynamics of quantum gravity. But incidentally, in this background, we know a full microscopic description of such quantum gravity, thanks to the pioneering work of Maldacena and colleagues something like 25 years ago. So we call this microscopic description of quantum gravity in the technical name of ADS CFT correspondence. It roughly says that the full quantum gravity behavior happening in this space-time is holographically described by a quantum mechanics or quantum field theory system living at the boundary of this space-time. So it's a kind of taking the form of hypercylinder. If you study the quantum field theory living at the boundary very carefully, it sees gravity as emerging in one higher dimensions. So using this description, we can try to concretely address the challenging thermodynamic questions of black holes. So it's a very technical thing, but it suffices to remember that very well-defined quantum system at the boundary can be used to study gravity, applying certain rules. And in simple examples, it turns out that the boundary quantum theory turns out to be certain gauge theories invariant under the gauge groups with large size. So if you consider UN gauge theories with n by n matrices, it has n square number of gluons. And this boundary theory provides a holographic description of gravity when the number of gluons becomes very, very large. So I'll be trying to explain some microscopic aspects of black holes using this description, especially report to you certain progress that has been made since this 25 years ago until recent. So before getting into any microscopic studies, let us try to summarize to you how the behavior of black hole changes in this antidistant space after introducing this kind of box. Again, the simplest thing is to try to understand the thermal physics of Schwarzschild black holes in ATS. Okay. For certain technical reason, people have done most studies on black hole, most extensive studies on black holes in ADS5 using four-dimensional quantum field theories. I think mostly for technical reasons, but similar studies can be done in different dimensions as well. Four-dimensional black holes using three-dimensional boundary quantum systems and so on. I explained this example because this is the most extensively studied one. Almost everything that I'm going to tell you is dimension independent, at least qualitatively. So if you take a look at the black holes in antidistant space, the behavior of the black hole becomes different depending on whether the size of the black hole is smaller than the radius of the antidistant space-time or whether it's larger. Okay, so in this case, energy is plotted by after making it dimensionless by multiplying the radius of curvature of this antidistant space-time. So you're plotting the Beck-Einstein-Hawking entropy of the black holes in terms of as a function of this dimensionless energy or mass. And depending on whether this quantity is much larger than or smaller than a particular dimensionless parameter, its behavior changes drastically. And the threshold parameter turns out to be n square, number of gluons. So if the energy, dimensionless energy is much smaller than the number of n square gluons, it behaves more or less similar to the black holes in flat space-time. Because, you know, the black hole, if the black hole is so small and the radius of the antidistant spacing is so large, the black hole locally visualizes itself as staying in an asymptotically flat space-time rather than antidistant. So its behavior for small black holes, smaller than the size of ADS, is exhibiting a concave entropy increase. It's really like the black hole we have been discussing so far. But if the black hole sizes grow and the black hole energies grow, and it becomes, if it becomes comparable or larger than the radius of antidistant spacetime, it suddenly feels that it's living in a gravitational trap, and it starts to behave more normally, like usual thermodynamic systems with convex entropy growth. So this is the characteristic behavior of Schwarzschild black hole in antidistant spacetime. When it's small, it's really like normal black holes that we observe in the sky. It grows, it feels the gravitational trap, and it behaves more like a normal thermodynamic system with positive specific heat. So that's the property of Schwarzschild black hole in antidistant spacetime. Concave and well, I exaggerated a little bit because if I really plot it with Schwarzschild ADS black hole, you know, you won't see the concave or convex behavior very well. So I decided to draw a cartoon to show you this convex and concave behavior more clearly. But if you, the same kind of physics can be seen alternatively by taking a look at the energy temperature curve, not the energy entropy curve. So the temperature, inverse temperature is obtained by taking a derivative of this. So if you plot the temperature and energy, and this is a real plot of ADS5 Schwarzschild black hole, the small black, the branch of small black holes with concave entropy increases is realized here. In the temperature energy curve, it's realized as a branch with negative slope, the negative specific heat. It's a branch where it's more similar to asymptotically flat black holes. But the black hole size increases at a certain point, after a certain turning point, it turns out to have a positive specific heat. And it's a genuinely new black hole in ADS spacetime, filling this ADS gravitational box. Okay. So the small black hole you can understand as an infrared regulated version of black holes in flat spacetime. The large black hole, which is a new object, you can really understand it as a new thermodynamic phase, which determines the thermodynamics of full quantum gravity at high temperature. Okay. So right after the discovery of this ADS-CFT, suggestion of the ADS-CFT, people have found what should be, people have anticipated what should be the thermodynamic interpretation of these large black holes in this holographic setup. So you want to interpret the meaning of these large black holes in this gauge theory with large number of gluons at certain temperature. So it's very funny quantum field theory. It's a scale invariant conformal field theory on funny space-time. But the thing is that being a gauge theory, it exhibits some features similar to what we know about QCD. QCD is a quantum field theory with a SU3 gauge group, n equal to 3, with some gluons and quarks. It's famously known to exhibit confining behavior at low energy, and the quarks and gluons are known to deconfine at high temperature, And although somewhat different in the details, this holographic quantum field theory in various different setups behaves sort of similarly as, in a sense, like the system of quantum chromodynamics. In that at low energies, the system confines, and it really forbids individual gluonic or quark degrees of freedoms to be excited. But if you increase the temperature, the system is expected to deconfine, and locally individual gluons are virtually liberated. Okay, so many thermal observables will directly see the contribution of individual gluons at high temperature. So actually, we expect a kind of sharp phase transition in this larger engaged theory. System confines at low temperature, system deconfines at high temperature. And very similar phase transition has been found in the gravitational side by Hawking and Page by considering these black holes in ADS and regarding them as representing the thermodynamic phase of quantum gravity. What happens at low energy temperature is that the thermal phase is dictated not by black holes, but thermal graviton excitations. But at high temperature, there's a phase transition, and the phase is dictated by the large black holes, thermally nucleated, which is thermodynamically stable. Okay? And this kind of question, the small black hole has no way to participate because it's an illegal object at fixed temperature. So with all these kinds in mind, Witten in 1998 made a very natural expectation that the two phase structures of quantum field theory and gravitational theory should be dual to each other. Especially, he naturally expected that the deconfined plasma of gluons and quarks, if there are, should be dual to the phase dictated by large black holes with positive specific heat and convex growth and so on. Okay. So that's an anticipation made in late 90s. It's very persuading scenario, but there are some challenges if you want to make this precise. So, well, I don't really have much time, so I'll try to be a little bit sketchy and brief. So the thing is that for quantum field theory to describe gravity in ADS semi-classically, the two challenging conditions have to be met. One is the fact that I mentioned already, it should have a large number of degrees of freedom, large number of quarks. I think one can motivate this as being, if you want to have a full quantum theory of gravity, you really need to have large number of degrees of freedom, let's say, to account for huge increase of entropy and so on. So it had better have large number of degrees of freedom. And another challenging request is that the quantum system has to be at a strong coupling. Because if you consider QCD or quantum field theory at weak coupling, you only see gluons at weak coupling, no gravity. So for gravity to be emergent at strong coupling, it had better be at strong coupling. And this makes the quantitative studies very difficult because we only can solve systematically the weak coupling regime. So in order to overcome this difficulty and get more quantitative lessons about these very fascinating scenarios of gravitational thermodynamics, from early days of ADS-CFT, people have tried to understand these gravitational thermodynamics in a supersymmetric or in a BPS version. Okay, so it's a hypothetical symmetry exchanging bosons and fermions, not yet having crucial experimental evidences. But you can, in this talk, you can merely view them as providing solvable models which keeps non-trivial physics of black holes and thermodynamics of quantum gravity. First of all, black holes exist, preserving this exotic symmetry. And this, although many physics are different from Schwarzschild black holes, some of their physics, let's say the behavior of entropies and the phase transitions and so on, are very similar to that of the Schwarzschild black holes. So you can regard really this as a solvable playground in which you can get concrete lessons about more interesting and wild systems. And thanks to the presence of this extra symmetry, you can really do a strong coupling calculations. So, well, just to make some story short, yeah. So in the kind of this supersymmetric models of ADS-CFT, one can circumvent the difficulty of the strong coupling problem, in which the energy levels of the system generally depends on coupling constants, so it's very difficult to compute. You need to really compute all the allowed energy levels at high energy to really compute the entropy at fixed charges and energy. But computing the energy level itself is generally difficult. But in supersymmetric models, Edward Witten have showed from early 80s that certain subset of states called BPS states have coupling independent energy levels. And in the ADS quantum gravity model at our hand, such states should have their dimensionless energy given by a linear combination of electric charge and angular momentum. And this sector turns out hosts spinning charged black holes, with which you can do very interesting black hole thermodynamics, somewhat similar to Schwarzschild black holes. Motivated by this kind of robustness of the spectral problem, these authors, something like 17 years ago, have defined and studied the supersymmetric analog of the thermodynamic partition states only, where you introduce two chemical potentials, one roughly corresponding to inverse temperature, and another to angular velocity of the black hole. So, yeah. So this is a very naive and innocent question. I mean, which any superstring theorist can imagine. So yeah, this is a kind of very naive question that any superstring theorist can imagine. You know, if you find a challenging strong coupling problem, very often there is a solvable, robust problem having to do with this extra magical supersymmetry. So people thought about trying to better understanding this black hole thermodynamics in ADS using this kind of robust spectral problem and this partition function problem, which you can compute and study at strong coupling. But for a few technical reasons, the success has been delayed until very recently. So very recently, meaning from roughly 4 years ago, people have studied this supersymmetric version of thermal partition function rigorously and quantitatively, and have got certain results which directly explains the microscopic physics of black holes. So technically, the free energy of these black holes is given this way. The C and A are so-called central charges of this quantum field theory in 4 dimensions, and they're all proportional to n squared. The fact that their free energy is proportional to n squared is strongly signaling the fact that the system deconfines and you know, getting contributions from individual gluons, right? And if you Legendre transform this function, you get an entropy which precisely accounts for the black holes known in ADS spacetime, spinning and charge. Just to give you some feelings, the general formula is very complicated, but at very large charges, entropy approximately given in this form, you can maybe easily see that if you really view them just collectively as charges, it's no longer concave. It's q to the 2/3. So it turns out to be convex behavior. So in the small charge region, it's concave. In very, very large charge region, it suddenly turns out to be convex, behaving like normal thermal systems. And you can really get confident by the various different ways that this system this system is about the supersymmetric version of the gluon plasma in the large engaged theory. Okay. So, sorry, I'm really short in time. So one small lesson that we get about this exercise, from this exercise on quantum gravity, perhaps is that, first of all, n square liberated gluons all contribute to the free energy rather than being confined. So it really quantitatively realizes Witten's expectation in this sector that the large black hole phase is due to the deconfined phase of gluon plasma. Quark as well, but number of quark is much smaller than gluons in this case. And it strongly also supports that the quantum gravity or string theory should undergo a phase transition at high temperature. And indeed, one can show that in this sector. It undergoes a first order phase transition, after which the gravity enters a very exotic phase. At low temperature phase, the traditional description of gravity is in terms of gravitons and some stringy and brainy exotic objects. But all these objects loses their meanings, just like mesons and hadrons almost lose their meanings at high temperature. Okay, so they probably have very strong implications of how quantum gravity should behave like, or maybe how our universe should behave like in very extreme conditions of high temperature or so on. So probably it will be very interesting if somebody can elaborate on this behavior of quantum gravity in extreme conditions, motivated by the behavior of very large black holes. So let me try to conclude. I try to explain to you two behaviors of black holes. One was the exotic black hole thermodynamics related to the fast increase of the high energy degrees of freedom of quantum gravity. And one was the normal thermodynamics of black holes, say if you introduce infrared regulator. And this normal thermodynamics of large black holes probes the new phases of quantum gravity at high temperature. Okay, and these two studies can be done, let's say in this ADS black hole setting, by studying the small black holes or large black holes. There are many more interesting questions along both directions, which I think deserves further extensive studies. And by now, it's quite obvious that novel aspects of these black holes provide good windows to better understand the structure of quantum gravity. I think it's quite providing us a good lesson. And of course, it will be interesting to see in the future if these new visions or viewpoints about quantum gravity turns out to be useful for understanding the real gravity around us. So this is a big question that I have little to say about. But after posing this question, let me try to finish. Thank you very much.
Thank you very much. So now it's time for questions. Okay, Nori, please.
No, I'm not asking. I'm just.
Oh, no, okay, sorry. Yeah, you clapped. Okay, it's confused. Okay, okay. So any question? Actually,
Okay,
yeah.
if you are allowed, I want to ask one small question. Can I just go previous slide, please?
Yes.
So when you say the naive picture of the graviton and so on change the description, is that what you mean is by duality? It is better described by the open string description. Is that what you mean, or are you saying anything more than that?
I don't think it's even open strings or, you know, let's say gravitons often described by, well, in gauge theory by gauge invariant operators, let's say some
Trace object,
fields,
right? Yeah,
maybe some derivative fields or something like that. So these are mesons.
Right.
And the fact that, I mean, these mesons are good variables at low energy and they are really closed strings. I mean, this sequence of contractions of fields and making a trace is making a closed string. But at high temperature, these are basically liberated into individual gluonic degrees of freedom. So it's not even an open string, I think. It's a full string bit.
Right. So that's what they mean by string bits. Is that right?
Yeah, maybe the minimal sized open strings in a very quantum sense. Well, so in this sense, it might look more close to open strings in that it has 2 gauge indices and 2 ends. But I think it's more drastic.
Can you make this mathematically more sharp? I mean, okay, I see what you mean, and I know what people are saying about this.
Yes. Yeah.
But I have a okay, rough understanding is okay, but how in the gauge theory, I mean, each phi ij which is not gauge invariant, how do you describe this in detail?
Well, that's what I meant by saying that the gluons are virtually liberated.
Right.
You know, still the gauge invariance is a good principle. So you have to impose a net charge being 0 condition for a very large operator. So the gauge invariance condition is imposed, but locally, if you go to very high energy,
yes,
you're allowed to locally excite some charge modes, which are subject to very mild singlet conditions. So that's what I meant by saying that individual gluons are virtually liberated locally.
Yes, I know. Yes.
So, well, I'm not sure whether it's quantitative enough, but yeah.
Okay. All right. Thank you. Thank you for nice talk.
Yes.
Can I ask a question about this? Okay, so it might not be appropriate for asking this question in this colloquium style talk, but I just want to know the detail of this. I mean, how to count the number of black hole microstate using this superconformal index. And okay, so if I remember correctly, even in the original paper by Huang and the company, they tried to compute this entropy of supersymmetric black holes using this superconformal index. But okay, so somehow when they are failed, I mean that in doing so, and what was the breakthrough? I mean that.
Okay, it's a technical breakthrough, but let me try to summarize it. So the thing is that this thermal partition function is a kind of Witten index which sums over bosons and subtracts over fermions. So if you successfully, I mean, if you compute this quantity and makes a Legendre transformation, you're going to get certain exponential of entropy as a function of certain charges. But it's a quantity which has to oscillate. It may be macroscopic bosonic number or macroscopic fermionic number. It's not just a positive large number. It's going to be a function of charge, which is macroscopic, but which will very quickly oscillate. So we can consider how this can be realized in this large charge macroscopic calculation. The thing is that you compute the chemical partition function as a function of chemical potential, and you do a Laplace transform, get this macroscopic degrees of freedom. What you expect to get is a macroscopically large number with rapid sign oscillations. And to realize that, what turns out to be the case is that if you do the saddle point approximation of this Laplace transform, is the Legendre transform. To realize this oscillating behavior, the saddle point of this Legendre transform has to be complex. And there are two mutually complex conjugate saddle points whose addition gives a very fast oscillating behavior. It's like the saddle point of approximation if you want to study these Airy functions, something like this. If you want to get these oscillating behavior of Airy function, there are always complex conjugate saddle points adding together to show this oscillation. So you have to search for a region in the chemical potential space which is complex to realize the sign oscillation for the index. But that was what has been missed by the earlier works. They just sought after the saddle points in the real chemical potential space.
I see.
So it's just that. I mean, once you relax that condition, you can get the modern.
I see. So okay, the guideline. Okay, so I think in that case, okay, we have to that make sure the rule. That of what kind of saddle should we pick up for this index calculation? Is there any established or rigorous rule for doing this? Okay, so it might be always a problem.
In the principle of saying what is dominant.
Okay.
Unfortunately, I think it's just empirical.
Okay.
They try to search for a real saddle point, which turns out to be just subdominant one.
Okay.
And we found new things which just explains black holes and.
No, I'm not that. Okay, so kind of offending, trying to offend you, but okay, I just wanted to know.
It's just the nature.
Sure. All right.
At least I think in very high charge regime or high temperature regime, I think one can argue that the saddle point that we found is dominant.
Okay,
but only in very limited.
Yeah, that's fair enough. Okay, I see. Thank you.
But mostly it's empirical. We found the saddle which explains black holes, so presumably that's dominant.
All these development using this saddle point approximations are kind of empirical. For example, like in the recent development, this island formula, we don't know what kind of saddle we should include. And if I include this effect of replica wormhole, then we reproduce the physical, but we are not sure why that we should include such a.
In general, it's very hard to establish whether certain saddle point is dominant or not. It's a global question. It can be answered only after finding all saddle points, I guess.
I see. Yeah. Thank you.
So, any more questions?
Can I ask a question? So your calculation is of course supersymmetric. So we don't expect some, instability of the state itself, but anyway, you have some thermodynamical instability. Do you expect some sort of instability when we slightly perturb your quantum states or?
Perturb my quantum states?
Yeah, so.
By going slightly non-BPS or what?
Yeah, slightly non-BPS. So maybe I'm not sure, but
yes, I
basically
think so,
for small black hole, you have entropy is like, convex, right? I think that's what you.
Concave or something.
Sorry, concave. Okay.
Concave means this,
Concave, okay. Concave means yes, concave, sorry,
yeah.
Right. But so for large, you find convex, right?
Right, convex, yes.
But the concave means unstable. And
thermodynamically, yes.
Yeah, so it's maybe, if you divide the black hole into two parts, maybe that's has a larger entropy.
What's the last thing you said?
Maybe, so so if we combine two black holes, then we have a larger entropy, like second law of black hole.
Yeah.
That's something opposite happens,
concave
right?
nature.
Something opposite, right? For small black hole.
For this, something opposite. So if you consider small black holes with let's say convex behavior, like let's say m square, then if you merge black hole, it has larger entropy. So the black holes want to merge. But
Okay.
for this, let's say, so in 5 dimensions, we had this and this. For large black holes, well, formally, it may look like that it wants to separate. But it's not really the case, but it's the black hole really filling ADS.
Okay.
There's no room for separating the two black holes.
So I just wonder some kind of fragmentation like behavior happens
Here for large ones.
because ADS2 black hole can happen, right? I think for
They can
ADS2
fragment, right?
fragmentation can happen so that it's space time is somehow.
That's right.
Yeah, I'm not sure. So, but the ADS2 is also common to supersymmetry. So,
Yeah.
maybe I find I want this is a very naive argument, but maybe you might have such a instability somewhere. But it's funny.
I need to recall myself. What's the physics of ADS2 fragmentation? I'm almost ignorant about that.
Yeah, I remember that only happens in low dimension. It does not happen in ADS3.
You know, the one comment, maybe unrelated to your question, but for strictly BPS states, thermodynamic instability is never attached to real dynamical instability. But for typical non-BPS states, thermodynamic instability is closely connected to dynamical instability. Because the dynamical evolution obeys the second law.
Yeah, I mean, the reason, of course, we are interested in small black hole to have some Hawking radiation, right, behavior. So but, I just wonder, something, I mean, some analog of that maybe happen even for supersymmetric black hole.
But even before going to Hawking radiation, I think if you start from this small BPS black hole and go to slightly non-BPS version of that,
yes.
It has classical tachyonic instabilities.
The tachyon?
Yeah. So if you consider some quasi-normal modes near BPS black holes, they have quasi-normal modes which grows, exponentially. So they trigger classical tachyonic instability for most of these. I think for all these near BPS.
Okay, so that means, so what's the end point of this instability?
End point will be some suitable.
Anyway, you have a lot of charge, right? So this charge should be preserved. So maybe small black hole, much smaller black hole, we get into some pieces of black hole.
Some cases identified as small hairy black holes. The general shape, I'm not sure. Well, but the thing is that the instability, the thermodynamic instability I mentioned is never happening at fixed charges, microcanonical case. At canonical ensemble, and the instability I mentioned just in the near BPS case was the tachyonic instability at fixed charges.
I see.
So I don't really have a sharp prediction on what should happen at fixed temperature for near BPS. Maybe it's still just, unallowed question. Yeah. At canonical ensemble, this is not really the saddle that people consider at all. I mean, it is just unallowed saddle. At fixed charges or fixed energy, they're completely fine because it's not coupled to heat bath.
I see. Of course, this is the charge, so it's a little bit different from usual.
So even after going to non-BPS, it's just illegal thing to consider. That's the best way to answer.
Okay. Yeah. Thank you very much.
Can I add some question in addition to?
Yes, please.
So this is related to your instability of the ground canonical ensemble.
Yeah.
So if the now M is Q, but let's restrict to the supersymmetric case. You never consider putting the temperature into the system. Yeah. But suppose you have Q and Q system whose entropy is Q to the 2/3, Q to the 2/3. If they combine, it becomes 2Q to the total power 2/3. But that entropy is smaller than Q to the 2/3 plus Q to the 2/3. Essentially, this is what you're saying, right?
Yes, this becomes I'm saying this. If you merge,
I thought it's three.
Oh, the large black hole. The large black hole, for large black holes.
Right, yeah, exactly.
It formally wants to fragment. It formally wants to fragment, But these large black holes are basically filling the whole box of ADS. So there's no real way of separating them spatially. There's an ADS box. These small black holes are really small, so you can really separate them spatially.
Right.
The large black holes are really filling the ADS, so you cannot really separate. It's like an ideal gas filling a box. Ideal gases really establish this convex behavior, but they all fill the box, so you cannot really spatially separate them. I think it's similar for the large black holes.
Oh, is that right?
Small black holes can be spatially separated, and this is of course disfavored. For large black holes, there's nowhere to separate this into, because large black hole is basically wanting to filling ADS trap or something.
Large black hole means that the size is bigger than ADS scale, essentially, isn't that right?
Right.
Does that immediately mean there's no other room at all to fragment? Okay, this is a bit.
Well, of course, ADS is non-compact, so but
I see what you mean, but looks like
ADS black holes are occupying a large region near the center of ADS. If you want to separate that, you have to displace it away from the central region where it's energetically. So it's a bit more exotic thing. I'm not sure whether this
entropy-wise, it's more favored. Is that right? Your argument show entropy.
But if you separate this large black hole from the center, I don't really know what its entropy will be like. It will be a totally different configuration than the original one.
I see.
I'm not sure whether this behavior will maintain or. Well, I'm just saying that there's no obvious way of naturally separating them.
Okay, I see. Because of the box of the ADS.
Yeah.
And this is essentially the nature of
gravitational potential carefully.
Right, but this is the nature essentially you were in the beginning for the Schwarzschild case as well. Is that right? This is power is less than 2. Well, no, power is less than 1. Is that right? I mean, negative specific heat and concave or something, which you mentioned in the beginning.
The Schwarzschild black hole belongs to the uppercase. It's concave. And if you put it in ADS, it's much smaller than ADS radius. So you can spatially separate them, but still the ADS gravitational potential is very weak. So you can approximately describe them individually as Schwarzschild black holes. But in the below case, it's impossible.
Okay. All right. Thank
you. Can I ask a naive question?
Yes, please.
So I think microcanonical ensemble is still well defined, even if it is applied to the black hole. Then you can observe your phase transition convex and concave in the context of microcanonical ensemble, for example, by looking at the density of states.
Yes.
So it corresponds to the free gluon and confined gluon, something like that.
You're asking how to interpret these
transition in terms
growing
of
entropy. What's the right variable to describe this macroscopic concave entropy?
So I can observe your phase transition in terms of the from the point of view of a microcanonical ensemble.
Yeah.
That is my question. How can you observe your phase transition in the context of
in the microcanonical setting?
Yeah, microcanonical.
How's the transition happening?
Yeah.
Here the effective variable should be hadrons. Here it should be gluons, and you're asking whether there's a sharp transition at fixed. If you increase the fixed charges.
Yeah, fixed energy.
Yeah, fixed energy, and just, I don't think there's a in this setup. I don't think there's a sharp transition. It gradually, this is smooth, and it gradually changes. So I think it should be just a smooth crossover if you consider microcanonical problem. At very high charges, it's fixing energy and fixing temperature is basically the same because of small thermal fluctuations. So at very high energy regime, you can effectively view it as described by gluons.
Yeah.
Here in this region, hadrons, but I think there's a smooth crossover between these two viewpoints.
Oh, I see. then, for example, if you try to apply the microcanonical ensemble to the Hagedorn transition, then can you observe the Hagedorn transition by looking at the density of state?
Hagedorn transition is a canonical transition, right?
So that's why I'm asking. So if you apply to the microcanonical ensemble, then can you observe the Hagedorn transition?
I mean, the only similar thing that I can say is the fast growth of the entropy when the description changes. Yeah, so the growth of the entropy in this region, well, yeah. I think the growth of the entropy in this convex region, this very fast growth of entropy, I think that's the remnant of the Hagedorn transition in this microcanonical picture.
Oh,
Yeah.
okay. Thank you very much.
Yeah. Eventually, this is what makes the canonical ensemble unstable. So
yeah. That's right.
So it's a singular of Hagedorn.
Yeah.
Close the colloquium. So we have already we have many questions. So let's thank speaker again.
Thank you very much.